In this section, we'll be looking at law of sines, law of cosines. Many of you saw this before, possibly in honors geometry or regular geometry. So we'll just take it a little bit deeper, good to review. What's nice about these formulas is they are able to work on any triangle. So it doesn't have to be just a right triangle. So Pythagorean theorem, SOHCAHTOA, your special right triangles only work when you have a right angle in the triangle. These rules here, though, will work on any triangle you have, which is pretty sweet. So here's your law of sines. It looks like this here. Sine of A over A equals sine of B over B. You can see you have an angle and a matching size, which you need there. For law of cosines, it looks a little more complicated, but basically if you break it down, and you can use other letters, but you have one side here which matches with the angle over here, and B and C would just be the other two sides of the triangle. So it's very useful when you know all three sides of a triangle and you're looking for some angles. It's also good when you have a side angle side situation, when you have two sides and the angle in between them. So let's see here. Here's how you can prove the law of sines. I think it's just kind of nice to see where it comes from. So you can see we have this triangle ABC. It's not a right triangle, so we can't use sine, cosine, or tangent. But if we drop down this height, this like altitude here, we then do have two right triangles. So I am allowed to set some things up. So let's see what we got here. For example, I could say the sine of A equals x over B. And the sine of B is x over A. So they both involve that side x, which means I can rearrange both of these. I can multiply by B over here. I can multiply by A over on this one. And we get something that looks like this. Since they're both equal to x, I could set these parts equal to each other. And with just some like little rearrangement, we get our law of sines, because I can basically here divide by B on both sides. So that crosses out the B's here. At the same time, I can also be dividing by A, and there we go. Okay. You'll notice in the actual law they have three ratios here. They're just showing you that all three angles can be used in this situation. It's not just like two of the angles. Obviously, when you're setting it up, you're only going to be looking at, like, for example, just A and B. You only need to set one fraction equal to another fraction. Okay. All right. Let's give it a go then, actually. So here's our situation. You can pause, you can read through it, but basically he's walking along, and we got some dimensions here. We are looking for angle Z in this situation here. So you notice it's not a right triangle, at least nothing tells me that it is. So I can't use my SOHCAHTOA, I can't use Pythagorean theorem. So let's go to another route. So I could say the sine of 32, right here, over 1,000. Those are my matching angle inside, is equal to the sine of Z, and across from that is 1,200. Solve this how you want to. Some people just like to multiply by 1,200 on both sides. I kind of like getting used to the idea of just cross multiplying in this situation, because often you have denominators you're solving for and whatnot. So solve it however you want to. But basically 1,200 times sine of 32 equals 1,000 sine of Z. I'm also going to have to end up dividing by 1,000 to get sine of Z here. This will just be, a number you can put in your calculator. Leave that entire answer in there because we want to try to be as precise as possible. And the last thing you're actually going to do is the inverse. So sine with a little -1 here denotes the inverse. We need to use an inverse sine function when we're finding the angle. So if you do the inverse sine of this answer, and if you're good, just type this last answer in, you should get your angle Z, which in this case is roughly 39.5 degrees. You could possibly even round it up to 40 degrees if they're asking for like the nearest whole degree. Let's try that again. So we got another situation. Again, feel free to pause to read through it. Basically, she's flying this balloon, and we got some angles, and we want to find, where is it? We want to find out how far apart they are. So you can call this X, or you can call it whatever. Actually, what did I call it? Oop, I'll do that. I called it X. So they're looking for the distance between them. So notice in this case, what I might actually do first is finding my missing angle. And I forgot to type that in here, but I could do 180 minus the 75 minus 60 to see what we end up with, which should be 45 degrees. And now I can set up my ratios. Let's see here. I use sine of 45 over X. So this angle over here is my 45. I can fill that in if that helps. There we go. So sine of 45 over X equals sine of 75 over the side here was 90. They said it was 90 long for the string. And once again, you're just solving, so you can cross multiply and all that good stuff, especially in this case when you have an X in the denominator. You're going to divide by sine of 75 eventually here, and just type that in your calculator. You get 65.9. I don't need to worry about inverses here or anything like that. I know all my angles. It was on the last example we had to do an inverse on. So they're roughly 65.9 feet apart. You can try this up on your own if you want to pause it. What I might suggest is when you were given information like this, sketch your own triangle. It is not drawn to scale here or anything like that. Piece, I've got to cut off there. There we go. Not drawn to scale or anything like that. We're just trying to visualize this. So like obviously n is not doesn't look like 105 here. So just drawing an idea of where everything goes. So when I look at this information, here's my triangle. Here's where everything goes. So I know what matches up with what. Now, to the nearest degree, what is measure of angle Q? All right, so let's see here. In order to find Q, though, excuse me, I actually have to go in a different route here first. I need to work with and find P. Because I said, oh, you know what, I drew this wrong. I'm sorry. P is 10 right over there. Now we're good. Because I don't know anything about Q. I don't know the angle, and I don't know the side across from it. So, sorry, across from P here is 10. My bad. So we set this up with sine of 105 over 12. These match up. Sine of P over 10. Because I don't know anything about Q, so I can't solve for it yet. So just go keep solving. You can cross multiply, or I just multiply both sides by 10 in this case. We get sine of P. I need to do an inverse, so we end up with P is 53.6 degrees. So now I know what this angle is. And since I know this angle, I can now find angle Q, because they just have to add up to 180. So subtract what we know from 180, so we get Q is 21.4. Now I can finally set up something else to find our side Q, because what is the length of side Q in this situation? I'm still going to go back and use this ratio, sine of 105 over 12, because that was nice numbers and they were known numbers. I'd rather not use that 53.6 since it's a rounded answer. Now the 21.4 I have to use because I'm looking for side Q and there's no other way to find it. So since there's no other way to find it, I'm going to have to use this rounded answer, but I'll just go with it from there. Again, I'm just cross multiplying here in this situation, and eventually I need to divide by the sine of 105, and then you can type that in, and you get roughly 4.5. There we go. Now, the other side of this law of sines is also the idea that there's this ambiguous case, which means like unclear. So let's look at what happens here. So they have this situation. They set up all their triangles. They're setting up their law of sines, and they do all the work we've been doing here, and they found their angle. Great, you know, this angle E here is 42 degrees. Cool. Here's a problem though. If you look at like the sine of 42, because you do this inverse here to find this here, sine of 42 would give you this number. The sine of 42 is this, but also the sine of 138 gives me this. These are supplementary. They both add up to 180, but they both give me the same value. So how do I know which angle it is? Maybe this angle E is 138 degrees. I know this is just a triangle they drew. It doesn't have to necessarily be set up that way. So we have to be aware that in some cases there might be a second triangle that results. It could be set up this way, or we could also look at it this way. If you look at the next page, this could be our angle of 138 degrees. Notice I still have a side of 8 and an angle here of 30. Or you could look at the big triangle of, you know, this is 6, this is 8, this is 30, and it's 42. So which way is it? Is this kind of small obtuse triangle, or is it this big acute triangle here? You know, which one is it going to be? This side here, that 6, kind of swing each way. So let's try that in an actual example here. So we have triangle ABC here, and we have angle A is 30, A is 5, and B is 8. So, you know, we want to find angle B, okay? And how many triangles are there? So I can set up a ratio, sine of B over 8 equals sine of 30 over 5. You know, keep solving like we normally do, cross multiply. We're going to end up dividing here. I get some value of 0.8, which I have to do the sine inverse on. So I get 53.1 degrees. So angle B could be 53.1 degrees. I can find that angle C, therefore, is 96.9. Again, this is not drawn to scale. This is just me setting it up to know where everything goes. Okay, but is there a second triangle? So to figure that out, find the supplement to B. Find out, you know, we found angle B was 53.1. But what does it supplement? Let's take 180 minus 53.1. You get 126.9. You'll notice that the sine of 126.9 and the sine of 53.1 should give you the same value. Okay, so maybe angle B is this. Oopsies, type something. Okay. Maybe angle B is this. And if I subtract these from 180, you notice everything else stayed the same. Angle A was always 30. This side was always 8. This side was always 5. I'm just seeing maybe this angle is bigger than what the other one could be. So if I find angle C, I was like, oh, well, actually, that could be possible. So like in this situation, angle C would actually be the biggest angle. So this would be like the biggest side. In this setup, angle C would actually be the smallest angle, and this would be the smallest side. If you try this out and you get like an angle that is negative, or an angle that, obviously these two, like, if they're too big, they add up to more than 180, then it doesn't work, and there'd be only the one triangle we have over here. But in this situation, we actually have two triangles. Right? I'm going to pause there, and we'll talk about law of cosines in another video.